In this video, we're going to look at phase diagrams. Phase diagrams give us a plot of temperatures and pressures at which a particular substance is in a particular phase. Now, what's kind of interesting about phase diagrams is that often we think about phases and phase changes in terms of temperature. That if I increase the temperature on ice, I can melt it and turn it into a liquid. If I keep increasing the temperature, I can boil or evaporate the liquid and turn it into a gas. But we really want to look at phase in terms of organization of the particles and kinetic energy of the particles. In the solid phase, yes, the particles have low kinetic energy, and yes, that would be a measure of temperature. If I increase the temperature, yes, a liquid has more kinetic energy, and so a greater temperature. But let's also think about the arrangement of the particles. A solid has particles that are arranged in a very organized, tightly packed structure. In a liquid, the particles are further apart, which they do have more kinetic energy, so they're moving around more. Phase is dependent on not only temperature or kinetic energy, but also the structure or arrangement of the particles, which could be changed by pressure. So that's what's kind of cool about these graphs, is that they'll let us look at phases and phase changes in terms of both temperature and pressure, both kinetic energy of the particles and arrangement of the particles. That's a good thing. So here's a typical phase diagram. Kinetic energy would be associated with temperature, and this particular phase diagram has temperature in Kelvin, which is fine. We'll often look at temperature in Kelvin when we're in the lab. We could also use Celsius, and Celsius plus 273 would get me to Kelvin. So when we're looking at this particular graph, if we see something that's like 273 Kelvin, it's kind of like 0 degrees Celsius. Pressure is measured here in units of atmospheres. It could be atmospheres. Another common pressure unit is kilopascal. And there are things that we'll look at eventually when we talk more about pressures. But for now, we can recognize that this atmosphere, ATM, is a typical unit of pressure. All right, so let's see what we can do with this graph. There's a couple different sections or lettered areas of this graph that we're going to walk through. Section A represents points where the substance is in the solid phase. Okay, so here it's listed as ice. So if this were water, we would call solid water ice. It could be anything in the solid phase. So I think we'll mark that in. Section A is solid. Now this particular graph is for water, but any substance will have a very similar phase diagram. This first region would represent temperatures and pressures where the substance is in the solid phase. And so now look at this graph. Here's what's kind of interesting. These are low temperatures. So the furthest point over, if I follow it down, like 273.51, if we want to get crazy. Well, this is virtually 0 degrees Celsius. Okay, so the furthest temperatures, the highest temperatures here, 0 degrees, which I know that's, oh yeah, interesting, the melting point of ice, if we're talking about water, obviously. So any temperature less than 0 degrees, duh, my substance should be in the solid phase, if this is water. But then look what else we have here. The pressure goes up pretty high. And so now this is kind of interesting. Here we're looking at 1 atmosphere. 1 atmosphere is kind of called standard pressure. And then this could go all the way up to 218 atmospheres. It's like some pretty high pressures. But if you think about it, at a high pressure, you're forcing those particles in a real compact structure, which should correspond to a solid phase. All right, so for any substance, this first area of the graph will represent temperatures and pressures where the substance is a solid. So what they're going to do on a test or quiz is say, at a temperature of this and a pressure of that, in what phase is your substance? You just plot those points on your graph, and if it falls in this first arena, your substance is a solid. Part B, any temperatures and pressures that fall in this midsection of the graph, your substance is in the liquid phase. Okay, so here it's listed as water. Let's be a little more vague and add liquid. Because again, this could be any substance. The middle section of your graph would represent the liquid phase. And finally, part C, beyond liquid, we are in the gas phase. So here it's got water vapor. Let's just put this in also as gas. This will represent temperatures and pressures where we are in the gas phase. And so watch this. Obviously, we're looking at higher temperatures. Higher temperatures, yep, I'd be in the gas phase. I mean, if I'm up here at like 600 and some Kelvin, that's like 400-ish degrees Celsius. Yeah, the water's in the gas phase. But this also brings up some low pressures. So here's my pressure. As I drop the pressure, I can also get particles in the gas phase. If there's less pressure acting upon the particles, they can be further apart from one another. And the lower the pressure, the more likely that the particles could be in the gas phase. Okay, so cool. A, B, C. And that's exactly the type of question that they'll ask you. At a temperature of blah and a pressure of blah, in what phase is my substance? So easy. Just plot the point on the graph and see in what section it falls, solid, liquid, or gas. All right, so let's look at a couple other lettered sections of this graph. Any points along line D? Okay, so look at line D here. It's kind of the intersection between solid and liquid, ice and water, if we're talking about H2O. Points along line D represent temperatures and pressures that result in both liquid and solid existing simultaneously in equilibrium. Whoa, okay, this is crazy. So we want to make note of that. We will have both liquid and solid existing simultaneously in equilibrium. If the temperature or pressure is changed so that line D is crossed, we will change phase. Melting or freezing can occur. Okay, so that's important too. Well, let me tell you this. Line D, this represents the melting point or freezing point. For a particular substance. And now we always say that, hey, water melts at 0 degrees, ice melts at 0 degrees Celsius. But what we don't often include is at a particular pressure. Oh. Which is often 1 atmosphere. And again, this 1 atmosphere, so here's kind of 1 atmosphere, That's often called standard pressure. So when you look up a chart of boiling points, melting points, freezing points for a particular substance, if I'm looking at water, it's going to say a melting point 0 degrees Celsius at 1 atmosphere. Because phase changes are not only temperature dependent, but also dependent on pressure. And so look at this. This temperature down here, we kind of mentioned before. This is virtually 0 degrees Celsius. About 273 Kelvin is 0 degrees Celsius. See, if I follow this line up, and I plot this point, we are right smack on the line between solid and liquid. That represents the freezing point or the melting point. And the difference is just the direction of our energy flow. If we're endothermically adding energy, then at 0 degrees, the solid will melt. If I'm exothermically removing energy, then at 0 degrees, my water will freeze. A liquid will freeze to a solid. But notice that the freezing point, melting point, changes depending on the pressure. So check this out. Like if we increase the pressure, so we're moving up the line, we're increasing the pressure, look what happens to the temperature. It drops. So like here way up at 218 atmospheres of pressure, that's a high pressure. If I follow this down, my freezing, melting temperature will be lower. Oh, interesting. Well, yeah, that's because if I'm increasing the pressure on those particles, I'm already forcing them to be closer to each other, which would be representative of the solid phase. That's like often if you're looking at, like your brownie mix or cooking instructions, they may have high altitude directions. Bake at this temperature at high altitudes, or bake longer or shorter at different altitudes. Atmospheric pressure will affect phase changes such as boiling or melting, freezing, condensation. Phase changes are temperature and pressure dependent. So anywhere along this line, if your point is directly on the line, you are at the freezing point or melting point. If I cross the line, the phase change has occurred. And the phase change can occur by either changing the temperature or the pressure. So if I were to increase the temperature and keep the pressure constant, I can change the phase. So at 1 atmosphere standard pressure, I can take a solid and melt it, or I could increase the pressure. So if I did something to increase the pressure, I could also cross that line from solid to liquid and keep the temperature constant. Interesting. Okay, so we got point D, or line D on the graph. Points along line E. So this will be very similar. Points along line E represent temperatures and pressures that will result in both liquid and gas occurring simultaneously in equilibrium. All right, so let's mention this equilibrium thing. Let's say I have a beaker of boiling water. The water is at 0 degrees Celsius, which would represent the boiling point Or it could be the condensation temperature, the condensation point. The difference is just the direction of the energy flow. Are we adding energy or removing energy? So let's say I'm watching a beaker of water boil. That'd be a blast. I check the temperature, it's 100 degrees. You will see both phases present. I will see liquid water and I will see water vapor. That's kind of this existing simultaneously in equilibrium. When you are at the boiling point, 100 degrees, you should see both phases present until the entire sample has changed phase. Now, technically, the same thing could be true of a sample of ice. That if you had a beaker of ice and you throw in a thermometer, your thermometer might read 0 degrees for a while. Even though you'll kind of see the ice start to melt. You'll see both phases existing simultaneously in equilibrium. You'll see a lot of solid ice, and you'll see some liquid water, like some of the ice is melting, but the thermometer might still read 0 degrees. Both phases are present until the entire sample has changed phase. And that's something that we're going to look at in the lab as well. So that's this existing simultaneously in equilibrium. If we are boiling water, we will see both phases present. And so if we do anything to cross this line E, a phase change will occur. Vaporization, condensation. Vaporization is just a general term for any change from a liquid to a gas, whether it's by boiling or by evaporating. Condensation would be the opposite. The gas condensing to a liquid. And so again, some interesting things happen. If I look at this point right here along line E, it's at standard pressure, 1 atmosphere. And if I follow that down, 373 Kelvin, 100 degrees Celsius. 100 degrees Celsius is the boiling point of water at standard pressure. And so if I have a sample of water, and maybe the water was at a lower temperature, and I increase the temperature, I can obviously cause the sample to boil or evaporate. If I cross the line, I change phase. You can also change phase by changing pressure. Oh, interesting. So, you could think of this in both directions. What if I have a sample of liquid water and I decrease the pressure? I could keep the sample at a constant temperature and I could change phase. You can even boil water at different temperatures. So for example, like often high altitude directions will take into consideration the fact that the boiling point of water is less. At a higher altitude, the atmospheric pressure is less. So if the atmospheric pressure is less, you can get those liquid particles to change to a vapor at a lower temperature. So the boiling point of water at a higher elevation might be like 90 degrees instead of 100, because there's less pressure forcing those particles into the liquid phase, where they're still relatively close to each other. And so if there's less atmospheric pressure, it's easier for the particles to become gas. It's easier for the particles to change phase. So I like these graphs. They'll show us phases and phase changes in terms of both temperature and pressure. That pressure component is kind of a big deal. And then finally, line F. All points along line F represent temperatures and pressures where both solid and gas exist simultaneously in equilibrium. If we cross the line, we change phase between solid and gas. And so this would be deposition. This would represent the change from a solid straight to a gas, or a gas straight to a solid. So that would be crossing this line here. Okay, cool. So now again, what they might do on a question is say, if the temperature changes from this to this, what phase change occurs? If the pressure changes from this to this, what phase change occurs? What line are you crossing? The line between solid and gas? Solid liquid? Liquid gas? That'll tell you the phase change. A couple other little points on the graph, two of them, G and H. Point G. We're going to look at point G in the lab. G is a special point. It's called the triple point. This is a special point where all three phases coexist in equilibrium. Whoa. We're going to experimentally look at the triple point of carbon dioxide in the lab, where we should get all three phases, solid, liquid, and gas. It's going to be amazing. And then finally, H is called the critical point. H is kind of this upper limit, where beyond this temperature and pressure, the difference between liquid and gas is indistinguishable. Essentially, we're talking gas for life. So if you're anywhere beyond this pressure and temperature, it's basically impossible to condense the vapors. The temperature is just too high. We're way off in this area. Gas for life. Almost impossible to condense the vapors. And so then here's the one that we're going to look at in the lab, carbon dioxide. And so again, any substance will have a similar phase diagram. It obviously doesn't have to be water, where the first region represents temperatures and pressures in the solid phase. In the center, we'd have temperatures and pressures in the liquid phase. And then finally, temperatures and pressures in the gas phase. Awesome. If we cross this first line, that would represent the phase change, melting or freezing, depending on the direction of our energy flow. Here would be vaporization or condensation. And then finally down in this region would be sublimation or deposition. The triple point we are going to get in the lab for carbon dioxide. It's kind of interesting. So the triple point is negative 57 degrees. All right, so that's cold, but manageable. And 5.1 atmospheres, which is a little bit greater than standard pressure, which would be 1 atmosphere. So if we increase the pressure, we should see some liquid carbon dioxide, and maybe if we cool the liquid, we can even get solid carbon dioxide and gas all at the same time. It's going to be amazing. Look what happens then if we follow one other point across, which is kind of an interesting point. At 1 atmosphere, which is standard pressure, if I follow it across and down, negative 78. And this graph is in Celsius. So if we have a chunk of dry ice, which is what we're going to start with, we'll start with dry ice, solid carbon dioxide, it will just sublime instantly. Instantly, it'll change from a solid straight to a gas. We'll be crossing this line at negative 78 degrees. At that 1 atmosphere, essentially this is the temperature of dry ice. negative 78 degrees Celsius. It's cold. But this is going to be awesome. You can't graduate from a high school chemistry course and not have played with some dry ice. That's exactly what we're going to do with it. Simultaneously, we're going to try to hit the triple point, where we will have all three phases existing at the same time. The critical point, I don't think we'll be able to create the 73 atmospheres of pressure. That's kind of a lot. But look at this, like at 31 degrees Celsius, which that's very manageable in the lab, gas for life. We won't be able to create this pressure, but this I think we can try to recreate in the lab. It's going to be awesome.